So hello everyone, and certainly welcome Tom. We're very excited for your talk. Tom Dietrich is, in my opinion, a giant in the field of AI. Um, uh, he's professor emeritus at Oregon State, and has had a very long career in AI, and I would say a prolific career in AI. Many hundreds or multiple hundreds of publications. A leader in robust machine learning, and more recently focused on safety critical systems, the use of machine learning in safety critical systems, which is what we're going to talk about. I've actually had the great privilege of being on National Academy studies with Tom. It's been great to work side by side with him, and even got to hang out with him a little bit at AAAI a couple of weeks ago. Tom is a former president of AAAI, so a world leader in the field. And again, we're really grateful and appreciative that Tom was able to join for our AI engineering speaker series. So with that, Tom, over to you.
Well, thank you very much for the invitation. At AAAI, I was also had a chance to chat with Tom Mitchell, who, of course, has done a lot of similar service things with the National Academy. And he said, yeah, when you finish the report, then you always want to write your own version of it. And so in some sense, this is my own version of the Machine Learning for Safety Critical Systems report that will come out and real soon now, that Matt and I were both involved in. So the plan is in three parts. The first part is asking how can we integrate machine learning into the traditional safety engineering processes. So as a machine learning person, I don't feel comfortable telling safety engineers how they should do things, but I do have a lot of suggestions for how the machine learning community needs to improve its technology to make it useful for safety systems. Then in the second part, I'm going to argue, following the lead of Nancy Leveson, that traditional safety engineering is not enough, and that we need to consider the fact that one of the reasons we're moving to machine learning is because we want to build systems that can operate in open worlds. And of course, all of our systems in reality live in open worlds, but we're often able to kind of work around that. But with self-driving cars, we're out there in the real world with all kinds of challenges. And so we need to think about the problems that come up there when we encounter novelty, when there are novel failure modes. And then finally, at the very end, talk a little bit about the need to approach the question of how do we achieve sort of longer scale resilience. And there I'm taking a cue from David Woods' work. He's retired from Ohio State, and works a lot from the human factors side. He likes to say resilient systems are systems that are poised to adapt. And so how can we build our safety critical systems in a way that they can rapidly adapt when new problems are uncovered? Okay, so just a review for about traditional safety engineering. My knowledge of this comes in almost entirely from serving on this National Academy study and reading Nancy Leveson's textbooks. But the central concept is that there is an operational design domain in which we can think of as the set of world states or system states where the system will be operating. And I'm going to draw examples primarily from the Wabi startup company. This is led by Raquel Otasin at Toronto. They're working on autonomous trucks for long haul freeway driving. And so that's our operational design domain is freeway driving. I don't know if they're putting restrictions on weather, snow, day versus night, but those would all be potential restrictions on the operational design domain. So once we define that, then we need to develop, of course, our requirements. Traditionally, computer science, we focus on our functional and non-functional requirements, but we need to now think about our safety requirements. And a typical thing, right, is to break the operational design domain into exhaustively into scenarios and then analyze each scenario. So we might think about a specific scenario where someone cuts in front of the vehicle and look at, well, what are the harms that could occur? And how severe would they be? How likely would they be? And then probably the most important lesson I learned from the safety engineers is there is no such thing as perfect safety. And instead, and it's also not up to engineers to decide how safe to make a system. Instead, that is something that society as a whole needs to decide through stakeholder involvement, through the insurance industry, through government and regulators to decide, well, exactly how safe do we need to make these systems? And of course, everyone points to the vast difference in risk flying in commercial aircraft versus driving to the airport. So society is willing to tolerate orders of magnitude more deaths on highways than we are in the air. Okay, well, once we have our requirements, and this is clearly a waterfall type of approach to design, then we can engage in the more or less standard V model or W model for design. So we'll be decomposing our requirements into subsystems, subcomponents, subroutines, and so on. And estimating as we do that how well we're doing at achieving this target overall risk level, and introducing safety mitigations such as redundant subsystems, redundant sensing, and so on. And building the tests and other verification plans for how we're going to verify the system as we climb back out after we've done the implementation. So time is going from left to right as this design shows. So the distinction is often made between verification, that is checking that the system that we've built meets the requirements that we articulated, and validation, which is checking that the system we built is actually the right system to have been building in the first place, which requires really engaging with users and simulation studies and so on. And of course, in some domains, we need to produce certification and documents to meet regulatory requirements. And then finally, we're going to be deploying, but this is where we'll pick up a thread later. Safety engineering continues post-deployment. So let's contrast that kind of a methodology with the traditional methodology in machine learning. So starting in the late 90s, around 2000 maybe was the peak, machine learning and data mining people were telling everybody in industry, the data that you've collected as a side effect of your business, your transactions, your medical records, your insurance claims, those are full of oil. Those are the new oil. That's big data. And we have tools that can mine that data and extract actionable insights. And that was the story we were telling. So it was focused entirely on existing data collected for other purposes. And just two examples of that, right? Probably the breakthrough data set that was created that led to the deep learning revolution was ImageNet, which was 14 million images harvested from web image sharing repositories, right? So those images were people documenting their birthday parties and their weddings and their vacations and so on, their sporting events. They were not collected for the purpose of building self-driving trucks. Similarly, the large language models, a lot of them are trained on the pile as well as other data sources. But this has, U.S. patents, medical literature, everything on Archive, Stack Exchange, Wikipedia, and so on. So clearly, again, data that was not explicitly designed for building a natural language understanding AI system. So a consequence of this is that if we build our say, computer vision system for a self-driving vehicle using that kind of found data, we have no guarantee that we'll be covering the operational design domain. We also have no guarantee that the machine learning system will construct a model that meets the safety requirements. In fact, the state of getting formal guarantees out of machine learning is fairly primitive. We do have statistical learning theory, but it only provides us statistical guarantees under pretty strong assumptions, usually that the data that we will see post-deployment comes from the same probability distribution as the data we trained on. But the distribution of the data we trained on is some arbitrary crazy thing. So that's never going to match. And so we really can't rely on statistical learning theory to give us guarantees. And of course, if the actual distribution in operations turns out to concentrate in a region where we had relatively little training data, the system will make arbitrarily bad decisions. So we need a new methodology for building machine learning systems for safety critical applications. And I think we should be ambitious. as a machine learning research community and try to achieve distribution independent accuracy. That is, we want to get away from these statistical guarantees and give stronger guarantees of good behavior for components constructed with machine learning. How can we do that? Well, of course, I don't know for sure, but one promising direction is that we should deliberately collect our training data to attain good coverage of all the cases, particularly the corner cases. And I'll talk about some work at WABI on risk-driven sampling techniques. I should mention the reason I'm relying a lot on WABI is they have been making a practice of every year at the CVPR, which is one of the biggest computer vision conferences, they give a whole day tutorial on what they're doing. And so they've been very open about their research contributions there. So we'll do risk-driven sampling to try to collect the training data that is most important for the application. And then I want to argue for formal verification of some properties of the learned model. And that may require us to draw additional training data in order to let those formal proofs go through. Okay, so how do we do this risk-driven sampling? The standard approach is known as surrogate model optimization, sometimes called Bayesian optimization. So of course, everything begins by collecting initial real-world sample. Say if we're doing trucks, then we'll be driving instrumented vehicles on a variety of highways in a variety of conditions, a variety of traffic levels, and so on. And we can train an initial machine learning component from that. In addition, and perhaps more importantly, we can build and validate a simulation model of the behavior of our vehicle, the behavior of other vehicles, pedestrians, I don't know, deer, kangaroos, whatever we need to model. And then what we want to do is we want to identify the regions in the input space where we don't have enough data. These are known technically as areas of high epistemic uncertainty. And unfortunately, most of the state-of-the-art machine learning models do not give us estimates of epistemic uncertainty. So instead, we'll often fit a surrogate model, typically a Gaussian process model, because the Gaussian process is one of the few Bayesian models that we can solve for in closed form. And so here's a one-dimensional example where the data points are these black dots here. The GP, the Gaussian process model, is the blue continuous blue line, and the gray regions are the sort of credible intervals telling us how much uncertainty there is at various points in the input space, which is this axis here. So the idea is that what the GP is telling us is that in this region, the curve could be doing other wild things. We don't know what the true function is. So we have a lot of uncertainty there, whereas at the data points, we're quite confident that we know the function. So using this, we can then define what's known as an acquisition function, which searches in the input space for points with maximum epistemic uncertainty, possibly other things like also maximum risk or other kind of coverage targets. And so we might select these three data points here, right? These three input queries. And then the question is, how can we collect new data points that correspond to those scenarios, if you will, those states of the environment? And this is where we rely on our simulation model to be able to simulate those states and determine what the outcome, how the system will behave and how it should behave. And metrics of interest are typically things like how well are we covering the state space, and also having very good coverage of the hazardous states or the boundaries between okay states and hazardous states. So I'm using hazardous state to mean a state where if the system enters that state, it has a high likelihood of causing a harm. So an example of this is this work by what they call Adversarial Simulator, or AdvSim, that was developed at WABI. So they collect scenarios of course, with an expert driver, in which they are collecting LiDAR data, also RGB image data, and radar data. But they focused in the paper entirely on LiDAR point clouds. And they build this sort of high-level description of the scenario. So this is our so-called ego vehicle, the vehicle we're controlling. This is a city bus, and the gray things are pedestrians, and the dots indicate the time series of motion. So the bus is stationary, ego vehicle is slowly inching forward. I don't know if you can see the slight color differences there. The pedestrian is crossing the street, and these pedestrians are going this way. So now the idea is to use this surrogate model to try to find a perturbation of this scenario that will break the current controller and cause a collision in simulation. And so, for instance, some of the moves that are available to the adversarial search are move the truck to a different lane. So I move the bus. So it moved the bus to this lane here, and had it drive away. And what happens then when they simulate that is it turns out that the ego vehicle drives forward. In other words, it did not see this pedestrian. It was just waiting for the bus to move. And the result is it collides with the pedestrian. So of course, the goal of the adversarial search for a scenario is to cause severe collisions, break the law, cause discomfort for the passengers in the vehicle, things like this. And it's important to note that the perturbation is being done at the level of these kinematic trajectories. So it's a fairly low dimensional space, relatively speaking. It's not 8 gigapixels, which was where people initially started working on very high resolution images. Instead, it's a much more semantic space that has fewer than 100 dimensions. And so they run but of course this requires, since they're operating in the sort of semantic space, they need to be able to simulate what the sensors would see. So they have to be able to simulate the LiDAR data for the perturbed scenario, then run their end-to-end system, which is a machine learning based system, score this adversarial loss for collisions and so on, and they generate they'll do for each scenario like this, they'll generate some number, say 30 perturbations, and keep the one that led to the highest adversarial loss. And then they will also do that for multiple scenarios, say hundreds of scenarios. And so what they found was that they could generate scenarios that greatly enriched the number of collisions. They got more than a 300% increase in collisions when we're running on these scenarios versus ones that were collected during normal driving, or I'm not sure, because their normal driving shows 8% collisions, which must not be, that's already got to be enriched by some edge case focus. Interestingly, there are also some slight decreases in the accuracy of the predictive components. So within their system, of course, they need to predict where each of the pedestrians and vehicles are going, first detect them, and then predict where they're going. And although that's not part of the objective of breaking the law and causing collisions, it turns out that the adversarial simulator does actually tend to find situations where the perception is less accurate and the prediction is less accurate. So then, of course, now that we've got these new cases, we can retrain the original model with the original data and our adversarial cases. And in the process, they were able to reduce the collisions down from 30 whatever down to 17.7%. They don't talk about in the paper iterating this, but of course, what you would do is continue to iterate this until you can find no more improvements in your system. And as a result, you will also have collected a huge data set of very difficult driving scenarios. The two notes I want to make is that, of course, is that this system is operating at the semantic level, which is very important, and that these collision rates in this data are much, much higher than would be expected under normal driving conditions. So we shouldn't panic when we see 17% collisions. That wouldn't happen in ordinary conditions. Okay, so what about trying to get guarantees out of this machine learning component? So how can we gain assurance that the machine learning system has learned the correct function? It's been trained on training data points that are actually in a very high dimensional space, say of LiDAR point clouds. So it's a very high dimensional space. How do we know that it's behaving well in between those data points? We have, the fundamental problem is we have no explicit specification of what the correct behavior of the ML component is aside from the training data. So can we come up with other properties that we would like that fitted function to obey or observe that would improve our confidence in the system? And one property might be that there's no wild fluctuations in between the training data points. So in one dimension, imagine that these orange dots are our training data, and the blue curve is the fitted function. And I've drawn it as a sort of jagged piecewise linear curve because that's the kind of surface that our deep learning models fit when they're using the rectified linear unit, which is a piecewise linear unit function. So I'm retired now, so I don't do research. I just propose dissertation problems. So here's my proposal for a dissertation topic for someone, which is, could we bound the difference between the fitted function and a linear interpolation of the training data? So let's consider two training examples, X1 and X2, and consider varying a parameter alpha and trying to maximize the difference between the blue curve, which is f of, we interpolate on the x-axis and then push it through the neural network, and we carve out the blue curve here, versus the orange curve where we're just interpolating between the two orange points. And the idea is to identify this huge departure here, this wild fluctuation in the training data. Now, I believe that this method can be solved, at least for smallish neural networks. There was a paper published by Singh et al. In 2021 that was pointed out to me by Zico Coulter at CMU, where they can handle proving a property over a convex region. And of course, this is a convex region here. The question is whether it will scale. And I think a key thing is we don't want to be operating in the convex region of the input space. We want to be operating in a semantic space of much lower dimension. So in particular, my proposal would be, of course, this looks great in one dimension, but for each known training case, I would propose that we identify the k most similar cases, which are training data, where k is equal to the number of parameters in the scenario. So if we have, I guess we had something like 7 entities or 6 in that scenario, and each one of them has a position and a trajectory they're going to follow. So let's say that's something like 60 parameters. So if we found our 60 nearest neighbors and then fitting a linear hyperplane to them is a sensible thing to do. And we can then ask over that entire hyperplane, what's the behavior of the blue function? Of course, if we find there is one of these bad behaviors, then we can construct a new query to the system, a new scenario, and simulate it and decide how the system should behave. And that will give us a new data point. And now we can train on that data point and presumably squash that bad behavior.
Tom, Eric has a question if you're okay.
Oh, yes. Go ahead, Eric. Yeah.
Yeah, thanks, Tom. So can you give me a sense of why piecewise linear is the target for this? It seems like, at least in your visualizations where you have these sort of regularly sampled training set or data, it sort of makes sense because there's a very small gap between training instances. But I would imagine if there's this large gap, piecewise linear would kind of fail you here. Is that just that we should
for the orange curve?
Yes.
Right? Yeah. It's a very good question, and I don't know. And you are absolutely right that in the point cloud space, every data point is very far away from every other data point. So and it's not clear that's certainly not the right space for doing the interpolation. But I guess I'm hoping that that linear interpolations here involve slight changes in the position of the bus, so we would be moving the bus smoothly here, and so on. And so they would be semantically meancome but why linear interpolation? It's the best idea I could come up with. Probably it won't work, and the student will have to come up with some improvements there. But and that may be that we do additional sampling so that the points to make the linear interpolation better.
Right.
But then that raises another question: was if the interpolation is really good, then why don't we use that instead? Because we know it's well behaved. So there are lots of interesting questions to pursue here.
Thank you.
And it could be other things people have looked at is bounding the Lipschitz constant in this region, right? And that might be another approach to solving it that doesn't rely on a comparison between right? I'm basically comparing two functions, which is, what we do generally in formal methods, but we could just try to prove certain smoothness properties of the blue curve. Okay, so if we're going to achieve this socially acceptable risk, we need to be able to estimate it. But we have discarded the training distribution. That is, we don't have, so how can we estimate risk? We've created a very weird distribution in which we are just constantly involved in accidents and crashes. So one thing we could do is just simulate system operation under normal operations and measure the probability of harm. But the challenge is the harms are extremely rare. Fortunately, that's the whole goal. And it's been estimated that we need 9 billion driving hours to do this. Now, I just saw a statistic that Waymo claims to have 11 billion hours of driving experience. So maybe they could get a sort of real world estimate of this. But a more efficient approach would be to use importance sampling to try to bridge the difference between the distribution Q of the data that is very greatly enriched for harms and catastrophes and the distribution P of normal operations. This does require that we build a model of the distribution of, say, the probability distribution over states in normal operations. And so that would mean the probability of, say, initial states, like where my car is parked in front of my apartment in the morning, the probability of the behavior of the system itself, which we obviously can do. We need to model the behavior of all the other agents in the world. That's going to be more challenging. But I think all of those things are doable. And then we need to, Q of S is going to be our proposal distribution. We could use the distribution that we constructed, from which we constructed our adversarial examples, but it may make sense to build a new distribution for this purpose. And then, of course, the idea is for each state we visit, where there was a harm, we multiply the probability of that state by this importance ratio. So if it's been highly elevated probability under Q, we're correcting that so that we only count it with probability according to P. And so there's a nice paper last year out of Michael Kochendorfer's lab, and probably many of you know that he is one of the leading people in safety critical systems. He's a professor in aeroastro at Stanford. And he's responsible for the current collision avoidance system that's been deployed. After he designed that system and implemented it, he spent 5 years doing verification and validation for that. So that was a Herculean effort. So in this paper, he now has a startup in automated aircraft. And so they wanted to estimate their failure rate for this task, which is visual acquisition of a runway on approach to the airport. And so they use surrogate model optimization to discover the hard cases for that visual approach. They wanted to explore regions with high operational likelihood, but also high epistemic uncertainty. So common cases where we don't have enough data, basically. And then explore regions near the boundary of the failure regions and explore the interiors of the failure regions. And so this is an example showing the number of samples from Q of S and how their corrected estimate, their importance sampling estimate of the probability of failure converged. And so we can see it's pretty much converged after maybe 400 or 300 samples, whereas if you were just doing standard Monte Carlo sampling, that is just doing normal operations, you would see 6 failures in 1,000 samples, whereas they saw 572 failures in those 1,000 samples. So you can see they're getting a much better estimate more quickly. Okay, so I think with these changes, we can integrate machine learning into safety and to this more or less standard safety engineering process. There have been arguments in the report that Matt and I worked on. There is also arguments that the safety engineers need to adjust to handling the how to introduce mitigations for the machine learning components, and that's definitely the other side. But from the ML side, I think we can support the scenario analysis, the design and verification of these systems. But Kochendorfer, when I was talking with him about this, he said, remind people, no single verification method is sufficient. You need to come at the problem from multiple directions with multiple tools to really build confidence.
Tom, Kiri Wagstaff has a question. Kiri is a member
Kiri.
of our advisory panel for the study, and I know a good friend of yours.
Hi there. Yeah, thanks, Tom. I just wanted to kind of build on what you just were sharing. Maybe it's related to the importance sampling thing as well, but it seems like with this approach, the real and the simulated data inputs are treated kind of first order, just mixed together. Are we comfortable with building safety guarantees or even just a safe system without distinguishing between them? Do we need to? Is there something we can do there to factor in the, simulated data is one step below what we can get from the real world?
That's an excellent question. And I have not seen, again, I don't have a comprehensive read of the literature, but the Wabi people never talk about how they validate their simulation. So I think that is a crucial step. I guess the challenge is validating the simulation as hard or harder than validating the safety of the design.
Right.
I think the simulator is likely to have a different fault profile than the controller will. So maybe it is something that can be done. But I think you're right. We need to take into account the weaknesses of the simulator too.
Related to that, do they or others ever talk about, say, what fraction of their training data was simulated versus real? They might report that.
I haven't seen that, but my guess is it would be huge.
Oh,
because
okay.
You can't go, you can't
Yeah.
collect real world collision data at scale without, terrible consequences.
Yeah,
There is an intermediate, right? There is a company that offers a closed track sort of physical world simulation where they have robotically controlled pedestrians and a track where they have occlusions and other things. And there's an interesting paper from Berkeley asking, okay, we have all of these queries we'd like to run. Which ones of them should we run in that track, which is somehow partway between simulation and the real world? And so that's that's it. Maybe there's some other intermediate steps like that we can do.
Yeah, thank you.
I think of training the astronauts in the swimming pools. It's kind of a similar.
I was thinking that too, so much of training for like aviation professionals is emergency scenario based. They go for the hard ones over and over, way skewing the distribution. It's kind of a similar idea just for training humans, right? With high fidelity simulators too.
Okay, well, now I want to shift gears and move over and argue that traditional safety engineering is not enough by itself. And here I'm really following Nancy Levison's book, Engineering a Safer World, right? In which she argues that when we deploy a safe system, we need to actively control that system to maintain safety. And when she's talking about the system and the controller, she's actually talking not just about the vehicle and maybe the driver, but an entire hierarchy of other human organizations that surround this deployed system. So we know that for things like Waymo and Cruise, they have human safety monitors that can step in and help the vehicle get out of traffic jams and things like this. There's, of course, the engineering team, which may be identifying problems that require software updates or hardware field modifications, recalls, and so on. There are government regulators all the way up to, say, the President of the United States. And all of them need to be involved in maintaining the safety of the system. So they are the controllers. What are the disturbances that they need to ensure against? Well, she spends a lot of time talking about the problem of budget cuts and staff reductions. She says that systems naturally tend to migrate toward the edges of safety. Why does she say that? Well, if you think about what management sees, if the safety engineers have done a great job during the design and manufacturing process, then the system will actually run for very long periods of time without an incident. And they say, well, why am I paying all these engineers and safety people when the system doesn't need this? And we don't need this many people. It's working great. And besides, I want to take this super talented person here and pull them onto some new project. And so over time, you tend to have staff turnover and have people with less experience involved. And you end up ultimately with problems like the Bhopal disaster, where there was a whole sequence of staff reductions in maintenance and so on, until finally some poor engineer makes a simple mistake that leads to more than 1,000 fatalities. So that's her point. I think the other kind of disturbance that we need to protect against is environmental novelty, changes in the running environment of the system. And that could be regulatory, but I'm focused mostly in the self-driving case on novel objects and novel agents, novel situations that might come up. And so we need to detect and compensate for those. And today, David Woods liked to emphasize, he claims we have never built an automated system that can adapt to novelty. Instead, it is always the humans and the human organization that brings that adaptive capacity. And I treat that as a challenge. Naturally, as an AI person, can we at least build tools to help humans do this? And so in particular, I want to focus on detecting novel failure modes. So some of you may be familiar with the high HRO literature for high reliability organizations that developed in the 80s and the 90s. And one of this is a group of organizational psychologists and sociologists studied human organizations that do achieve very low rates of faults in safety critical situations. And they catalog what are the practices that those organizations use to achieve that. And one of them is a fundamental belief that there are unknown failure modes of the system they're monitoring or controlling. And their job is to try to find those failure modes before they cause harms. And their key performance indicators are how many anomalies have we detected this month? How many near misses have we detected this month? And if those numbers start to drop, the assumption is we're not looking hard enough. We need to be digging deeper and try to detect more of those, because we have a fundamental belief that there are failure modes out there waiting to bite us, and we need to find them. So what is the status of AI methods for detecting anomalies and near misses? Well, in computer vision, I've been, for the last 10 plus years, working in this area. And I co-authored a big survey paper led by Lucas Ruff that appeared in Proceedings of the IEEE and done some work at Oregon State. And I think it's safe to say that in advances in deep learning and particularly in vision foundation models, that is, vision models have been trained on vast amounts of imagery exhibiting huge amounts of variability, that these are producing major improvements in our ability to detect novelty and anomaly. But also we know that no method can guarantee to detect all novelty. I mean, there could be, I don't know, invisible aliens out there that none of our cameras can see that we could collide with, or things like this. Just as a side note, there's a company called artificio.org in Peru that collects imagery there to use for testing computer vision systems in the developed world. They find scenarios like this where construction workers have just put out concrete blocks instead of traffic cones to indicate a construction zone, things like this. Okay, so I think there are two kinds of hazards that we need to consider. The first set being perception failures because of novel objects or novel imaging conditions, and control failures, near misses. And so novelty detection in machine learning is a pretty well-traveled area. I think fundamentally it comes down to defining a good space in which we have a good distance measure so that anomalies show up as outliers that are far away from the training data. So if these points are our training points, and this is a query point that comes in a new image, if it's far away from our training points in this space, then we would say that's a potential anomaly. Sometimes people argue instead for fitting a probability density to these points and then using the surprisal, the negative log probability, which I view as a kind of way of normalizing the density, the distances, because fundamentally everything relies on having a distance of some kind or a base measure like the Lebesgue measure. For deep anomaly detection, a big advantage of deep learning is that it learns its own internal features. We don't need to do manual feature engineering. And that's good because, of course, Euclidean distance in pixel space is not useful at all for detecting novelty. But the problem is deep learning only learns the internal features that it is forced to learn by the training task that we give it. And those features may not separate novel queries from nominal data. And just to illustrate this, some work by my student Alex Geyer, we trained a dense net, which is a kind of computer vision deep net, on 6 categories of objects from the CFAR 10 benchmark set, holding out 4 categories to be novel things that the learning system did not see. And then we visualized what's happening in the internal representation. And what we see is these darker colors are the known categories of objects. These are images each of a known object. And the green ones, the light green ones are images of novel objects, which of course the learning system is not seeing. We're just asking how is it representing them as it's learning. And what we see is that the known classes, their representations are kind of pulled out of the center of the space and then clustered into nice clusters. And we can see that a classifier then can easily separate these points in this space. But the surprise to us was that the data points corresponding to novel objects are still pretty much in the middle of the space. They have not, because the system didn't train on them, it wasn't forced to build distinctive representations for them. Now, to some extent, distance still works because these are, in the middle of the space. They're somewhat far away from the training data points. But we can also see there are a lot of cases where the novel objects are overlapping known objects. And in those cases, the learned representation will not be able to detect the novelty. So what can we do about it? Well, this is where the foundation model approach comes in. By training on not just 6 categories of objects of known objects, but say 6 million categories of objects, or all the training data we can get our hands on, including artificially introduced variations, and maybe we hire some, crazy artist to design stuff, Joan Miro, bring him in, whatever, to design synthetic data, train a deep learning system that builds a representation that can represent all of that. Then when the system sees a novel object, such as a one wheel, which didn't exist when ImageNet was created, it can say, yes, I recognize that this is a skateboard, but it has a very fat wheel. That combination is something I've never seen before. But I do know how to represent the fat wheel. I do know how to represent the skateboard. And so I have the features that I need to detect the novelty. What about near misses? I think this is an area, there are 2 cases to consider. Of course, during the design process, we worried about the known hazards, and we've introduced margins of safety so that the system avoids parts of the state space that are close to those hazards. So we can, if we have the right sensors to estimate our state properly, then we can tell when we enter those near-miss regions, and we can detect them. And of course, this is what's done in aircraft. If 2 aircraft come, too close together, that's an incident that needs to be reported to the FAA. But the difficult case is what I call counterfactual near misses. So imagine that our self-driving vehicle has a requirement that it always maintains at least a 2-meter separation between itself and pedestrians, cyclists, stationary obstacles, and so on. And now consider a case where a pedestrian is in the crosswalk here, and this self-driving car is coming toward it, and the pedestrian decides, I don't think that car sees me. So he runs out of the way. The car comes through. The car measures its separation and says, I've got my 2 meters, no problem. But this is a counterfactual near miss in the sense that it would have been a safety violation if the pedestrian had not taken evasive action. This is pretty subtle because, of course, pedestrians, don't enter a crosswalk if they see a car coming. But that doesn't count as a near miss. So defining this exactly right is a challenge. But I think we have Pearl's theory of causality that he's developed over the past 30 years that gives us a formal basis for computing these near misses. So this is my second PhD thesis proposal, is someone should be looking into this. And I think once we've identified that we have a novel failure mode, then, for each of our near misses or anomalies, we need to diagnose, well, what's the cause of that? And I think that could be challenging, but of course, in artificial intelligence, we've been working on diagnosis and repair for the last 40 or 50 years. So I think we have a long history of methods to take advantage of. And certainly for a novel object like my one wheel, we can collect data. So you can imagine a self-driving car say, oh, there's something new. Let me slow down for a minute and take a bunch of pictures of it so that I can learn about it and recognize it in the future. Okay, and just then to wrap up, I want to talk about safety as continual redesign, or resilience as continual redesign. So many people have observed that engineered systems have this property of being robust and yet fragile. They're robust to the known hazards because we design them to be robust to the known hazards. But unfortunately, they're often vulnerable to novel failure modes. And one explanation for this comes out of this theory of highly optimized tolerances that was developed at Caltech. And the argument goes something like this. We have the known hazards, and now imagine this is now our kind of feasible region of the design space, not the state space anymore. So we rule out certain designs because we know that they have a risk of causing harms. And then having identified those additional requirements, we then optimize for size, weight, cost, and so on. And when we do that, that pushes the design toward the edges of the feasible region of the design space. And unfortunately, if there's an unknown hazard lying just outside the states, this diagram isn't really quite right, but that could push us into states in the state space that come very close to unknown hazards, such that a small disturbance could cause us to fall into those. And this is presumably what's behind things like, if you look at the cloud compute providers, I guess we call them hyperscalers now, but Google and Amazon and so forth, they have some of the very best reliability engineers on the planet, and yet they still suffer multi-hour outages of these huge cloud data centers. And David Woods has been doing some consulting studies with these hyperscalers to try to understand why. And part of the reason he argues is that the information needed to detect the novelty is not all available to a single person or a single sub-organization within these large organizations. The information is scattered across the organization. And so he argues that the people need to practice communicating horizontally and do this regularly so that they can get better visibility into what's going on. But he also, as I say, articulates this idea that a resilient system is one that is poised to adapt. And here he's thinking the human organization needs to practice adapting and be poised to adapt. But an AI perspective on this is we have some design space that we went through when we designed the initial system. We followed some trajectory through that design space. And then, of course, the initial design goes through some field modifications, so maybe it moves around a bit in this design space. But I think, and early in my career, I worked on mechanical design problems in some collaborations with Boeing. And our focus there was on design rationale capture. So we wanted to just document why the decisions were made in that initial design. But I think a new view would be that we should build an AI design tools for this design process, well, design tools in general for this process, that we can keep running on hot standby at all times. And so whenever we're making changes to the design or whenever we encounter a problem where we need to build a revised design, we have the system already running, already fully loaded with all the documentation so that we can make that change quickly. So in summary, I talked about how we could make machine learning safe for safety critical engineering. I think that relies on high fidelity simulations, risk-driven generation of the data, and then formal verification of properties of the learned model. And then I backed off and talked about the need to detect novelty, either anomalies or near misses, and that I think we have AI tools for detecting anomalies, at least in the computer vision side of things. But the problem of near misses is something that is pretty much been ignored in the AI literature. And then finally, I think we should embrace a vision where our design tools are not used only during the design process, but are really an integral part of our ability to adapt in real time to the systems as they change. In some sense, I guess it's sort of like what people aspire to with digital twins as well. So I'll stop here and answer questions. Thank you very much.
Yeah, great talk, Tom. Thank you so much. We do have some time for questions, so I'm hoping we get a few. I see Kiri and then Holland and then Carol. So Kiri, go ahead.
Oh, that was just me applauding. I guess it probably
Oh,
wasn't
those
the
are
right hand.
claps, not hands. Sorry, they're very small on my screen.
Yes.
So you got lots of clapping, Tom. Hopefully we have a
thank you.
question or a few questions. Andrew.
Hi, thanks for the presentation. It's extremely informative. Coming off a project that's looking at a lot of the similar issues, and so looking to hear more. One of the things that I don't have a good understanding for from a safety space, but I'm particularly interested in, is like the fail-safe kind of things going on, especially like considering 7009, and how it talks about the use of AI actually in the fail-safe mechanisms and in the safety mechanisms. Do you have any thoughts on that?
No, I'm not very. I haven't thought very deeply about it. It seems to me that having a safe mode is not always possible, or does require some reasoning. There was a sort of notorious traffic accident that occurred very close to Corvallis, where I live, 30 years ago, where smoke from a fire blew across the Interstate 5. And occluded the views of the drivers. Drivers entering that smoke cloud hit their brakes and people hit them from behind. Because your first reaction is a safe mode is slow down and pull off to the side of the road. But the safest action in this case was actually to just continue, because the cloud was actually pretty small, maybe 20 meters wide, and you'd come out the other side and be safe. But instead, I think there were maybe 17 fatalities. It was a catastrophe. So, of course, we can't avoid all such collisions, but there was also the problem with the cruise vehicle in San Francisco that trapped a pedestrian underneath it, and the vehicle believed that it was still in the traffic lane and wanted to pull over to the side of the road. So it dragged that pedestrian, I think 12 feet, 20 feet, something like that. And we can see that was an accumulation of several problems. But it was an attempt to move into a safe mode. But they didn't have sensors underneath the vehicle. No one had thought to put a camera down there or figured out how to keep it clean, to detect that there was a person under the car. And there was a state estimation problem. It was already actually by the side of the road. It didn't need to move at all. And so those are my two kind of anecdotes. Did that answer or address your question at all?
Yeah, sure. I just wonder if you had any observations or thoughts about it. So thanks very much.
Yeah, I mean, it does seem to require reasoning about the situation to decide what is the safe action to take. And this is a decision made under huge uncertainty. And so maybe there is maybe we can't, because it's under uncertainty. I think a super important point that I didn't skipped was it's critical that our perceptual systems provide a quantification of their uncertainty, so that the vehicle make its decisions not based on the best guess, but based on the uncertainty, and say, okay, if I'm uncertain whether there's a pedestrian there, I better slow down and creep up, and if I have an ability to illuminate the scene better or what have you, maybe I should do that. So figuring out how to do that decision making, the controller under uncertainty, seems like a very important thing. And we have a huge challenge in producing good uncertainty estimates from our machine learning models.
Oren.
Thank you very much for the talk. I really enjoyed it. I was hoping to get a sense for how you're thinking about scale for some of these approaches. So you talked about, I think it was the surrogate optimization using Gaussian processes. If I remember right, those scale very poorly in the number of samples you have, or distance or surprisal when you have very high dimensions. How do you deal with those problems?
Well, there's been quite a big industry on scaling Gaussian processes, so I think that can be addressed. At least in terms of fitting the GP. but then you have to search in that space to find the high uncertainty regions, and so that there you do have a scaling problem. And let's see, your other question I lost.
The like distance and surprisal.
Yeah, so yeah, I think distance in the for anomaly detection is as you say, it's problematic. There's a whole raft of approaches people have followed to do that. One thing that's interesting is doing deep density estimation, which allows us to do some dimensionality reduction and model those things. In our work on novelty detection in computer vision, we actually didn't use a distance-based method at all. We used a method based on what we called familiarity. What we discovered was that when you train something like a ResNet or a vision transformer using supervised learning techniques, each classifier for each category basically learns to look for features that are characteristic of that class. And so it's sort of just adding up estimate of how many features for that class it sees. It's surprisingly not discriminative, and it's not looking for evidence of other classes or for negative evidence so much as positive evidence. And this means that you can use the so-called logit score as a measure of familiarity. If the logit score is small, it means that the classifier for that class didn't see very much evidence and for that class is present. And if all of the classifiers for all the classes say, I don't see much that's familiar here, that's a signal that there's something novel. And that does not rely on a distance measure. So I think there are prospects for dealing with things that way. But when you use self-supervised methods to do the learning, this property is no longer observed. We now see that there are lots of irrelevant or noise features that need to be downweighted by the classifier, and it's more difficult to interpret the signals.
Okay, thank you. Thank you again for the talk.
Well, Tom, unfortunately, we're at time. I think there's probably a lot more conversation we could have. I want to say thank you again. Very much appreciate you making the time to give the talk. It was a great talk, very informative. I think it will inform our study in multiple different ways and in multiple different directions. And thanks for sharing some dissertation ideas. There's a few folks on the call that are likely to pursue their PhDs, and maybe they'll take up one of yours and certainly reach out to you if they do so. So thanks again, Tom. I look forward to seeing you again soon and getting that National Academy study report finished, which would be amazing.
It would be good, yes. Okay.
All right. Thanks
very
again.
Much, everybody.
Have a great weekend, everyone. Take care.